All right, so once again, I want to make sure Zoom attendees, can you hear us? Good?
Yep.
Yeah.
Yes.
Anyone? We couldn't see the text there. All right, if anyone can unmute yourself.
We
just
can hear
let me
you.
know you're good.
Yeah, can we hear you?
Huh,
All good.
is it because of the voice?
You're getting chats. We're saying, yeah.
Okay, so the chat says good. Okay, but we don't hear anything. Okay, but okay, good. So welcome to the engineering seminar series offered by UW-Platteville. So the engineering seminar series are designed to showcase from the design to the construction to the maintenance of projects of not only civil engineering but also other engineering projects, and then to showcase how we make it happen, how the projects make our world a better place. So today we are very happy to have Michael Hikins from the electrical. Okay, I'm going to read it here. Electrical Consultants Incorporated. I'm a little surprised that because we don't have a lot of in-person attendees. I thought it's not a busy time, but that's okay. We have a lot of people from the Zoom. I understand Zoom is more convenient, but thank you for coming, both in person and on Zoom. Thank you for your time. So I will give a very quick, brief introduction to Mr. Hikins, and then we'll get started. So Mike is a licensed professional and civil engineer and serves as director of transmission engineering for Electrical Consultants Incorporated. Mike is an experienced overhead transmission line engineer and provides technical oversight for all of the ECI's transmission design teams. Michael has been responsible in supporting energy developers and electric utility in the interconnection gigawatts of renewable energy throughout the United States. He has participated in industry committees such as updating the SC Standard 48, the design of steel transmission pole structures. So Michael is based in Madison, Wisconsin. So without further ado, please help me welcome Michael.
Yeah, it looks like we have 61 people on Zoom as well now too, so
Yeah,
great
awesome.
turnout.
Awesome.
So thank you, and it's great to be here. Again, my name is Mike Hikins. I'm the Director of Transmission Line Engineering for Electrical Consultants Incorporated. And excuse me, we like to get out and talk a little bit about our company, especially to non-electrical engineers, because there is a fair amount of civil, structural, site work, a lot of other engineering that goes into the power system as a whole. And sometimes our name, electrical consultants, may be a little misleading, but we call ourselves ECI for short, to make that not so much of a mouthful. But today I want to talk about the US electric grid, and I want to talk about interconnecting one of the largest solar plants in the country in California. And so the presentation today is going to be kind of focused on two distinct areas. One is the US power system and talk about how renewables work in that system. And the other portion is going to discuss some specifics of the project itself and the challenges and complexities of trying to interconnect these types of projects. So I can advance my slide here. There we go. So the objective today is to provide everybody a basic understanding of the US power system, of the US electric grid. What is it? What does it mean? Kind of provide a basic understanding of what an ISO and an RTO is, and also balancing authorities, the impact renewables have on grid operations, and then just the general challenges of transmission line design and integrating the infrastructure that is required for these systems, those challenges to integrate that into our physical world. So a real quick plug about our company. So ECI, we've been in business since 1985. We are a national leader in power delivery engineering. We do have a subsidiary company called EPC Services. This is where we can offer full turnkey design build type project execution, both union and non-union. Between the two companies, we have roughly 750 employees nationwide. In Wisconsin, we have roughly 85 people based in our Wisconsin office between Madison and Green Bay. And we really like, we have very good luck. I'll plug the university, very good luck with University of Platteville graduates. We like to come down here and hire candidates out of university. We've always had good luck there. So real quick, some of this may be a little bit remedial for some, maybe not so much for others, but I'm going to go over some really high level components of the US power grid. This is an insert from the Wall Street Journal. And basically, it all starts with the generation. So in the power system, obviously we have power plants, whether it's thermal, solar, geothermal, et cetera. We want to generate that electricity at relatively low voltages, but to transmit the electricity long distances and not have a lot of losses associated with it, we need to transform that energy to a higher voltage. If you think about a conductor, like the overhead wires that you see when you drive around the street, those have a fixed resistance. We can buy a larger diameter conductor, but generally speaking, the resistance is fixed. There's not a lot we can do. Unfortunately, mechanics of materials, those scientists and those engineers haven't brought us really ultra low resistant conductors yet. So we have to work with what we have, and that is primarily aluminum for overhead applications. So because of that, we want to transmit energy at a very high voltage, 345,000 volts, 500,000 volts, 230,000 volts, because we can pack more energy per unit, per electron, and push less current down the conductor. And the losses are basically current squared times the resistance of the conductor. So we really want to reduce the current that we're pushing and increase the voltage so we can really transmit a lot of power, power being power being the current times the volts. So we're going to step that voltage up, that power up to a high voltage. We're going to transmit it across the country, wherever it needs to go. When we get to more local areas, neighborhoods, schools, etc., we're going to step that voltage back down to a distribution level. Distribution level voltage is going to be around 25,000 volts, 25 kV, maybe 12 kV, depends. From that voltage, it's going to be stepped down again before it goes into the end user. For a home, it's going to go down to 240 volts. You're probably familiar with that. To a school or something, a commercial, maybe 480 volt, 208, but in any event, significantly lower than the transmission voltages and the distribution voltages. And this is all about trying to maximize the amount of energy we can transfer through the system while minimizing losses associated with transmitting that energy.
2 gallons of super paint, agreeable, Greg?
Cost the environment. So we really want to try to drive those losses down. Overall, the US electric system can be broken up into 3 primary components, right? So we've got the Eastern US grid, we've got the Western grid, then we have Texas or ERCOT. And each of these grids function almost independently from each other. They are generally connected with each other in certain specific locations, but in general, there isn't a lot of energy transfer between the grids themselves. Part of that is some of the grids are, let's say, they're not quite in sync with each other. And we'll talk about the synchronization of the system and the frequency of the system a little bit later. But at these connection points between each of the grids, there are AC, DC, AC converter stations. Basically what that's doing is we're going to take the AC power, we're going to convert it to a DC current. We're going to re-rectify it back to an AC current so we can get get it synchronized together so we don't have any either out of phase or low frequency issues between the two systems. But in general, I think it's just good to understand there's basically 3 major components to it. Then we also want to introduce this term. It's called a balancing authority, and a really key component to the electric grid and electricity in general is that we have to consume exactly the amount that we produce. We have to produce the exact amount that we consume. In other words, we can't really store it. We'll talk a little bit about some battery energy storage a little bit later, and the Sanborn project certainly has utility scale energy storage. But as a general rule of thumb, the amount of energy consumed has to equal the amount of energy produced. That's a little different than, say, a water utility that can build tanks. It can store water in case of a rapid drawdown due to a fire or due to just large demand. Or say other energy providers like natural gas or coal. We can't have coal stacks of electricity per se. We can't have tanks full of electricity like we can for natural gas. So that's kind of a interesting component of the electric system. You have to produce what you use and you have to use what you produce. If you don't, bad things can happen. So we have these things called balancing authorities. There's 66 of them in the US, and they're charged with ensuring that the system itself is balanced,
So
that
then you're
extra
telling me how
generation in
these are
one
supposed to be
location
used.
is being
And these were
transmitted
kind
to a
of,
location that
well,
needs
once
it,
you
and
figure
vice
it out,
versa.
you gotta put it in hot water first.
Kind of one step
Yeah.
deeper
Mute
into
your
it,
mic.
beyond just the three major components, we have the independent system
Mhm. You have to
operators
put it in hot
and
water
or the
first. You know
regional
what it looks
transmission
like.
organizations.
I would even say a
And
full
these are
minute.
basically
If you're on Zoom,
entities
please
that
mute your
sit
mic.
a level above the typical utility. And here in Wisconsin, we fall under what's called the mid-continent ISO. And basically what that means is there's a bunch of utilities that operate in the region, and the ISO helps coordinate the flow of electricity between the various utilities. It also helps serve as a market manager that can help market participants participate in the more deregulated market of bulk energy transfer. But in general, they're a balancing authority across multiple states as well as multiple utilities. Our project, the Edward Sanborn project, is located in California. So it's regulated by the Cal ISO. So Cal ISO is the independent system operator for California. And they're going to be the ones to balance that energy. They're the balancing authority for California. Again, we can see ERCOT in Texas. You guys might be familiar with that terminology, given they had some problems a couple of years ago with some outages in their territory. And I'll talk briefly about that as well. But in general, the United States is structured this way. And in those white areas where there isn't an ISO, that's really where the balancing authority is just the utility itself. In the Western United States, it's much more, a utility can have a very large geographic presence in just a very large geographic area. Whereas in the upper Northeast or the upper Midwest, it's more dense, there's a lot more utilities, and you may have a whole bunch of entities that need kind of a higher level of coordination. And that's really where the ISO can come in and help facilitate the flow of power between the individual utilities and ensure we have a stable system. So what happens when it doesn't work the way we want it to work? And we'll just briefly touch on this. So when the balance of supply and demand is no longer being met, it's problematic. Again, like I said before, the amount of energy generated needs to be used, and the amount of energy being used needs to be generated. Those have to work together. If not, we run into a frequency issue, and this is a little blurry, but basically in the United States, we operate at 60 hertz frequency. And when we begin to differ from that frequency, there's a lot of problems in the system. It can damage equipment, it can damage motors, it can damage something as simple as your refrigerator that maybe you're at home. It can damage the auto manufacturing plant. So maintaining frequency is very important. It can actually damage the equipment inside the substations that are responsible for converting the energy. And so the utilities are very, very keen, and the ISOs are very, very keen to keep frequency within a safe margin. And so in Texas case, they were seeing loss of generation at the same time they were seeing an uptick in demand. Generation was being tripped offline because it was very, very cold outside, and some of their plants may not have been properly weatherized for a cold weather operation. Obviously, demand is going up because it's cold. We're running heaters. We got resistive heaters like a space heater, things of those natures. All of a sudden, we're seeing where we have more demand than we have capacity, and therefore, this frequency begins to drop. And this just illustrates what has to occur by the ISO. So as they're losing generation with time, and you can see it, if you can't see it, I apologize, I'm a little blurry on the Zoom, but at 1:23 in the morning, ERCOT issues 1,000 megawatts load shed. So the ISO, the independent system operator, is going to go to the electric utility and say, you need to disconnect 1,000 megawatts now. And the utility has a plan in place, right? They're not going to turn off electricity to a hospital. They're not going to turn off electricity to the airport or to other important loads. They have a plan in place for when that order comes down from the independent operators, in this case, ERCOT, of who they're going to shed load. Most likely, it's going to be residential users. At 1:33, still having problems, but it's stabilized a little bit. So from 1:23 in the morning to about 1:43 in the morning, 20 minutes or so, they're back to ordering additional load shedding. So around 1:43 a.m., ISO says we need to shed another 1,000 megawatts. Meanwhile, they're also losing generation as the plants are tripping offline. When they finally get down to 1:53, they are shedding another 3,000 megawatts they're ordering to be shed. They go a couple of minutes later, they ask for another 3,500 megawatts to be shed. So basically where they were at with this particular ISO was they had about 5 minutes. If they would have operated at 59.4 hertz for 4 minutes and 23 more seconds, then more generators would have tripped offline. The frequency would have went down even more. It becomes basically the system collapses in on itself. So bad things happen. So that's kind of the reason we want to make sure that we keep everything in balance with each other. It's not a presentation on the what happened in the Texas freeze, but I think it does give some context to how the ISOs and how the RTOs kind of play into the markets and can kind of help maintain stability in the system. So moving on, I wanted to go into California itself because that's where our project is, and I wanted to talk a little bit about supply and demand. So we've covered, we have to keep demand and supply the same. So what we're using, we have to be producing, and what we're producing, we have to use. So this is a typical demand curve in California, for CAISO, which is a system operator. I pulled this information. This is all public on 3/23 of 2022. And so hour 0 is the middle of night, it's midnight. At 1 a.m., you can see from hour 0 to hour 5 or 6 a.m., demand is pretty low. It picks up in the morning, very common. People wake up in the morning, they're going to turn on their television, make their coffee, whatever you're doing, take a hot shower, etc. Going to see an uptick in demand throughout the day. The demand begins to subside again. That's very typical to have a midday lull across almost all ISOs. We see that. California, it's a little bit more pronounced because we also at the same time, we see uptick in rooftop solar generation. So some of the big box stores, maybe some of the other large point loads aren't needing as much energy as they were earlier in the morning because now they're producing their own on-site solar. But then what really is interesting and what happens, and again, this is consistent across most regions, is we see a strong demand peaking around 7 or 8 o'clock at night. And then after that period, the demand begins to fall at a relatively quick pace. So there's this curve at the end that we see as people are returning home from work, they're doing a lot of things. They may be doing plugging in their cars, they may be turning on the washer machines, or they're cooking dinner, they're doing a lot of things. Maybe they're watching television. And so we see a pretty strong uptick in demand at that time of day. So what does the supply side look like? So I said earlier, we have to match demand and supply, they have to match, right? So what does it look like on the supply side? So again, on the exact same day, 3/23 of 22, CAISO, we can run the report and say, okay, what did the demand look like? The supply look like for that day? Well, if we look at it, it's interesting. It's not a nice, smooth, even curve that we saw with the demand. But what we can notice is the red line would be imports. So in this particular ISO, they don't generate enough energy within the ISO, within their area to satisfy demand. So they import it from neighboring utilities. That's not atypical, that's normal. They also have a fair amount of natural gas generation, which is described by the orange line. The green line is the renewable sources. You can see that in the middle of night, generating just a hair under 3,000 megawatts. And then anybody could probably guess what happens at about 7 o'clock in the morning And what happens at about 7 o'clock at night, sun rises, solar generation really picks up. This is only really applicable in California in their Cal ISO system. No other ISO at this point has developed and penetrated this much solar into their system to the extent that CAISO has. And this is atypical to their region. Again, there's a reason why our project the project was developed where it's developed. The other base load, you can see the black line at 2,000 megawatts. That's the sole remaining nuclear reactor, Diablo Canyon in California, producing steady state base load energy. And then there's some hydro resources in there, as well as some other coal and things like that are very, very small for California. One interesting line, and we'll zoom into that in a little bit, that's the battery trend, the yellow line at the bottom. And if it's below the line, it's charging. If it's above the line, it's discharging. I think a nice takeaway from this image is to show the relative scale to each other, right? That the batteries, as many have been deployed at a utility scale, it's still relatively small compared to the overall scale of the supply. So if we break out just solar separately, because that's really what we want to talk about with Sanborn Edwards, is the solar side of production. And there's a couple of really good benefits to solar, right? One is very predictable. We have a really good idea of when the sun's going to rise, and we have a really good idea when it's going to set. So we can plan for it. We can have those other resources available to bring on generation when we need it at these particular times of the day. The wind curve is a little more variable, but actually pretty consistent. It's the blue line going between 1,000 and 2,000 megawatts. Again, we see some biomass, biogas, small hydro. Those are almost really aren't a big contributor to the renewables trend. It is purely solar generation in California, topping out at about 12,000 megawatts at peak output. Battery side, wanted to talk a little bit about this as well. So same day, 3/20/2022, we can see that throughout the evening, the batteries are really not doing a lot. They're adding, taking away, probably just capturing little dollars in frequency. But you can see that during the peak hour, when we're really generating a lot of solar, we're charging the batteries. And then when it gets to the evening, we're discharging the batteries, which is exactly what their intended purpose is. The last chart as it relates to CAISO on the demand side of things is just Cal ISO. They have so much renewables on their system, they actually produce what's called a net demand trend. And really all this is, it's taking their demand and it's taking out the renewables and basically saying what's left. So what do if I've got my demand, let's take out the renewables of it, to supply the renewables. How much extra do I need to either purchase on the open market, do I have to generate via a combustion turbine, etc. And obviously it's inversely proportional to the supply side, and the demand side are going to be inversely proportional on this in this case. So again, if you look at the red line, you can see a pretty steep ramp up. In fact, it's actually really, really steep. It's 15,000 megawatts in 3 hours is what they need to ramp into. And that is occurring because at the same time that solar energy production is exponentially decreasing because the sun is now setting, that's the same time that the consumer is using a lot. Their demand is really going up. And if we keep in mind with Texas, what happens when that demand and that supply begin to get a little bit out of whack? Well, we have to roll brownouts, and indeed California has had to do that previously because they were unable to dispatch enough electricity on the open market to meet their demand as their solar system was decreasing. So the battery is really going to come in here and try to pull that solar curve to the right and try to lessen that 3-hour ramp and kind of flatten everything out. But there is one large wrinkle in the system that we're still trying to fully understand, and what is the impact of an EV going to be? Now, certainly we don't want to have everybody drive an EV, everybody who is driving an EV come home and all plug in at the same time, because that's just going to push our peak even higher. We're going to have that ramp is going to be much steeper. So, you know, the utilities are talking about how they can try to manage that by having folks charge at different times of the day. But I think it's really interesting to see the curves on top of each other and really see what is actually happening in the market as it relates to the renewables and why these projects, why there is such a gold rush out in industry to build these projects, get these projects online. So I don't know if I pause for a second if anybody has any questions on what I've just covered, and then we'll get into the project itself.
So
Yeah.
are you saying that there's way more demand than what we can produce right now?
What I'm saying is there is way more demand than the renewables can produce. And so the difference between what the renewables can produce and what the demand is has to be made up by a different source of energy. And in California's case, it's likely going to be natural gas generation, or it's going to be imported from an adjacent utility.
And what about like the carbon dioxide affecting our atmosphere? How does that come into play when it comes to finding energy?
Well, certainly burning a fossil fuel is going to produce carbon dioxide. So again, I think these types of projects, the solar projects that don't produce carbon dioxide when they generate, if we could put more of that energy on the system, I think you would see that there would be less of a need for the combustion turbines or the gas turbines to do what they're doing. So that would reduce those types of those carbon dioxide emissions. But they don't, the important takeaway is the solar plant doesn't run 24 hours a day, right? It runs, in this case, basically 12 hours a day. It produces a lot of energy in 12 hours, but it doesn't run for the full day. If there's any other Zoom questions we wanted to address or just move on.
Yeah, I don't see any
Okay.
questions from the Zoom. I think we can keep going and then until we have the questions.
Sure. So kind of set the table, so to speak, with the market and what are we doing with this stuff and how does it fit in? And so here's the project, I guess, the main event, so to speak. So the Sanborn and Edwards project, what is it? It is a utility scale solar generation facility. The technology utilizes photovoltaic, which is relatively new. In some old plants, that was actually a thermal, where you just use mirrors to heat up a sodium liquid, and the liquid we heat with boil water and turn the turbine. These are photovoltaic, similar to what you would find on your roof, just utility scale. There's also a utility scale energy storage system, battery energy storage system called BESS. That technology is lithium ion. Nameplate capacity of the entire facility, both plants, roughly 1,400 megawatts. So again, if we remember that previous curve, California is producing about 12,000 megawatts. So this is going to be roughly, 1,400 out of the 12,000. It's going to be 10% of their total output in this one project. To accomplish this, we need to construct two 34.5 kV to 230 kV collector substations, and then we need to interconnect this resource to the electric system somehow. And that's also kind of a big difference with renewables, and is oftentimes where we go to get the resource, the renewable resource, that's not adjacent to the electric grid. In other words, we're a really good place to plug into the electric grid that works electrically, that works from limited environmental impacts, not having to build a lot of infrastructure, oftentimes is not where the resources are located. So we have to build infrastructure between the two to connect them. Project location, it's out in the Mojave Desert, located just north of Los Angeles. There's actually a lot of resource development, renewable resource development out there. The project itself is roughly described by some of these KMZs. So the green would be the rough area of the Sanborn panels where they would be located, solar. The other pink is the Edwards plant, with the yellow just representing some cultural sensitive areas where we can install any panels. The black line represents the transmission assets that need to be constructed and built back towards the point of interconnection, which is located in the upper left corner of the screen. And that is, quote unquote, the plug into the grid. That's where we're going to inject the 1,400 megawatts into the system. So the challenges of the project are, how do we connect the generation assets, which are located to the east, to the interconnecting substation to the west. Real quick, just a switching diagram of what this kind of looks like. So this is, we've got multiple circuits coming in. So each plant's going to generate enough energy. It has to be put on 2 separate power line circuits. So we'll have 4 incoming circuits total. We have 2 interconnecting circuits that go into the interconnecting point. It's a real simple switching diagram. Basically, energy is coming in. We're going to meter it. We're going to put a circuit breaker in there, protect the equipment devices. We're going to have some switches, and then we're going to send it back to the point of interconnection. This is probably a little small to really see everything, but that's basically what's going on. Is the energy is coming in. There's devices to protect the equipment, protect the circuits, just like you'd have a circuit breaker in your house. We're also going to meter it, so we know how much energy is flowing through the system at any time, so we can manage if we have spikes or drops in it or anything like that. Plus, we want to revenue it, so we get paid as well. So what would be some big constraints on the project, and what are things that you typically have to work through to interconnect something like this? In California, for anybody who's done projects in California, who knows a lot about California, California is a very heavily regulated state. They have a lot of rules. The state of California is very proactive on a lot of environmental requirements. So what does that mean to the project? A little bit more time to work through the process, and sometimes a little bit of cost associated with it. So from purely a transmission side of things, we have a highway and a railroad crossing occurring at the same time. There's areas where there's very constrained right-of-way, which means the transmission line itself has a very limited corridor to fit through. An interesting area in here is there's the LADWP, LA Department of Water and Power. They have large HVDC transmission line and large AC transmission line that we have to cross. The other interesting tidbit is there's the aqueduct located there, which is the Los Angeles Aqueduct, and that serves, there's 2 of them in this project site, and that serves obviously drinking water for the LA area. So we have to cross those. The point of interconnection is challenging. It's a very large facility. And then there's just a fair amount of complicated electrical metering requirements, which we won't really get into, but basically with the battery systems, they're either front of the meter or behind the meter. They can be DC connected or AC connected. This project has a little bit of everything. So the substation, this is one of the substations to interconnect the facility. So basically, what we would look to do here is we have all the generated electricity that's going to be, so take a step back on the solar plant itself. The solar panels are going to generate the electricity in DC current. That DC current needs to be converted to AC current before it can be transformed to a higher voltage, so it can be transmitted to the collector substation. So that voltage is going to be 34.5 kV. That's very common in industry for collection voltage. Collector voltage is going to be brought in, it's going to be metered, and we're going to put it through another power transformer to convert to the system voltage. The system voltage for this area is 230,000 volts. It's 230 kV system voltage. So the collector substation it's doing a lot of different things. It is collecting up all of the various circuits of energy from the generation field that can be miles in length. And it is, in this case, it's providing some current limiting support to prevent devices from suffering from short circuit problems. We're going to transform the voltage to the system voltage. We're going to meter it, and we're going to put protection devices on there in case there's an accidental fault. We can trip the system. The Sanborn substation, very similar thing. It's going to do the same thing, except it's going to look at the Sanborn site. Some of the challenges with the project and some of the design considerations that need to be taken are crossing the highway. So with overhead transmission lines, for engineering mechanics, right? The force times distance on our moments. The higher we put the load up in the air, the more overturning moment we're going to induce at the base of the foundation. And so when we have these long span and we're crossing over these roadways, it definitely adds cost. It also adds a certain level of coordinating with various agencies. So the Caltrans and the county, they have their requirements for crossing. Also the railroad companies are going to have their requirements for crossing. In addition, from a constructability perspective, there's going to be a lot of coordination to close the freeway or close the highway and allow and make sure we're coordinating correctly with the rail traffic so that we're not going to be installing the conductors at the time frame when we're crossing over the road. So it does create a lot of complexities to it. This one is particularly challenging because there's 2 railroads to cross as well as the highway and some distribution circuits that are located out there as well. Another perspective of that crossing, you can see the solar array being constructed in the background. That's what kind of looks like a lake off to the distance. And then the crossing of the roads on it in the railroad. The aqueduct is an interesting component. So Los Angeles Department of Water, they really want to have very high clearance requirements over the transmission assets, over their aqueduct. They want to be able to run large equipment up and down their right of way should they have to ever do any maintenance or any work on the aqueduct itself. So what that does is it requires us to design these very tall transmission towers. And my point, what I was saying before, is when we have to do this, the moments become very, very large and the steel poles become very, very heavy. And it's challenging from a structural engineering perspective to even get sections large enough to be able to carry the moment and the shear that's induced by this. And so these are 2 images of what that looks like being constructed and then after it's being built. These are 210 feet tall to get over the LADWP aqueduct. And what does that look like from an engineering perspective? So the left side is the plan and profile for that particular segment of the transmission line. You can see on the left side of the profile view, at least, the conductor sag, generally located in this area down here, to get up and over the LADWP aqueduct. We need to use, like I said, 210-foot tall structures to cross over and then come back down to meet the requirements. The aerial imagery, you can kind of, there's 2 of them, you can kind of see the outline, the left and the right side of the aqueduct. They're actually underground in this location. Some parts of the aqueduct are above ground, but through here it's all below ground. The right side is just a KMZ Google Earth view of what that would look like. So what would we do to, what sets the height of these? Some of those questions. It's code driven. So depending upon the operating voltage, we would need to maintain safe electrical clearances to ground. We want to ensure that any vehicles or any people or any items that are underneath the transmission line aren't going to be exposed to any dangerous electrical shocks or magnetic fields, electric fields, things like that. So that's really what's going to set the elevation. Again, the aqueduct owner, Los Angeles Aqueduct, they want a lot of ground clearance, again, so they can run heavy cranes basically up and down their right of way without any need to coordinate with the utilities that have built assets over their facility. So they want to be able to dispatch their maintenance crews and their construction crews, knowing that they've got a lot of safe working clearances to do their work. The constrained right-of-way portion of the project, another interesting tidbit of California, is there are what are called franchise road agreements that can be utilized. And so the current county, which is where the project is located, they have a really narrow road right-of-way. It's primarily been built to house distribution circuits. And renewable developers have seen that they can put their transmission assets on those same right-of-way locations to save costs, primarily because a lot of the landowners are really not willing to let you build that infrastructure on their property. Interesting problem with linear type construction, whether that's highways or gas pipe, pipelines or transmission lines, is getting the landowners that you're going to impact to have them see benefits in that the infrastructure you're proposing to build. And that's always a challenge. And so a lot of landowners are maybe apprehensive to allow linear infrastructure to be put on their property because they don't see there's any benefit to it. They don't get, it's not like a shopping mall that may add property value. It's not, a new road that might be able to let me subdivide. It really is something that it is hard in a lot of cases to express that benefit. It kind of comes down to the benefit of the broad versus the benefit of the individual. But so oftentimes that's problematic to get right of way for transmission lines. California certainly is no exception. So there are these existing public right of ways that can be utilized. And to do that, in this case, there's significant challenges in getting the transmission line to physically fit within those right of ways. So it really requires us put all the circuits stacked on top of each other and very, very tall type transmission towers and keeping that within the public right of way. Excuse me. So foundation design considerations for these types of towers. Obviously, like I spoke earlier, the taller structures create significantly higher overturning moments. Large diameter piers are going to be on the order of 10 feet. The moment demand is going to easily exceed 16,000 foot kips at the base, with a shear demand exceeding 700 kips. So when we see those types of loads, we would compare those to like the gravity loads on a bridge or in a building. Those kind of overturning moments are very atypical for a lot of other types of civil type construction. And transmission line design, 16,000 foot kip overturning moments to design your drilled shaft is somewhat typical. These are a little bit bigger given the height of them, but that's not an unheard of amount to try to manage. Construction creates a lot of other issues out on site as well. So as we go from the drawing board, from design to actually try to get this built, again, in those constrained right of ways that I showed earlier, this is a typical type of a drilling rig that would be required to install a roughly 10-foot diameter pier. It's somewhat impactful to do that. And so we want to be cognitive about the types of items that we specify, but there's physically enough room to build them. And so I kind of just wanted to show, some of the scale of even getting the foundations into the ground. So this transmission line also, we think of most of our transmission line design as being in an overhead position. In some cases, it's buried. In this particular project, there was a need to bury a portion of the transmission line. We were not, the project developer was not given, and it's common that the DC circuit would not allow them to construct any assets underneath their circuit. So there was a small section that we had to bury. Underground transmission is somewhat complicated. It seems like it'd be straightforward, just bury some cable in the ground. The issue is we need to protect that cable. There are grounding concerns. There's a lot of other electrical items that go into the design of that, but in general, it is as what it sounds. You're going to go from a bare overhead conductor into transition into an underground insulated cable. And this was very challenging for the project, as can be seen by all of the underground cables. So what happens with when you bury a circuit, there's a lot of thermal heating that occurs, and the earth acts like an insulator. And so whether we're using copper or aluminum, the material itself, if it gets too hot, will change the property of the material, right? Copper will melt at some point. Melting probably not going to occur at normal operation, but what can happen is it can anneal and it can begin to change a little bit under the earth. And so we don't want the conductor to get overly hot. And when they're looking to move as much electricity as this project is proposed or is moving, trying to bury the conductor is very complicated in the sense that it's very difficult to manage the thermal issues associated with the buried conductor. And so what had to happen is this entire excavation had to be backfilled with a thermal type of a backfill. It's a type of concrete that is designed to help move the heat out of the system so that the cables don't overheat themselves. So this required a very large trench to be opened up to help accommodate this. And, you know, I'm a transmission line engineer. I don't mind the look of the lines. Obviously, it's what I do, but I can definitely understand why the public may not like the looks of the lines. To bury this type of infrastructure is not necessarily, well, one, it's not very cost effective, and two, there is a lot of challenges. You can see the size of the people down in the hole there doing some of the work. So it can be very impactful to bury higher voltage, higher current type of projects. And obviously it's very expensive. So yeah, you can see the drilled shaft foundations. This is the conduit that the cable would be installed in. A lot going on there. So with that, I think I saw a lot of Zoom chats come through. Maybe the best thing to do is maybe to jump into some of those.
Yep. Any other questions from here in person? Good. Okay. Here, I'll do this. So looks like we've got quite some questions here. So
Pull it up here.
yep. So Murray asks, does this say that every means there is yearly a cascade fail or a necessity to have brownouts because of the sudden drop of the supply versus sudden increase of the demand?
It doesn't mean that. It's a good question. And so when I said earlier that it's predictable, we know the sun is going to set every night. We know what time it's going to set. And so what can happen is the ISOs have already procured electricity to fill that in. So they go out and they basically sign contracts with electric generators and say, okay, at this time in the night, I'm going to need this much electricity. And so then they come in there and they begin filling in what the solar plants are not doing. What had happened previously when it got really, really hot in the West, I think it was last year, the adjacent utilities didn't have as much surplus energy to sell to California. And so there was just in general in the entire region, a lot of demand and not a lot of supply. And so in that case, that ISO, since it doesn't have enough of its own generation kind of within its territory, it is somewhat susceptible to the availability on the open markets. And almost always there's sufficient capacity in the open market to fill their needs, unless there's some severe weather events. 10 days of 100+ degree weather can deplete those resources. So to answer your question, no, because they've procured energy because they know they're going to need it. Battery nameplate capacity is 1,400 megawatts or a solar capacity. So I don't have the actual battery energy capacity itself. They're still building that portion of it. I don't have a final number, but the actual output, the maximum output is 1,400 megawatts. And so what that means is if I've got a bank of batteries that are, say, fully charged up, and my solar plant begins to generate less than 1,400 megawatts, I can begin to discharge the batteries and maintain that 1,400 megawatts until my batteries begin to degrade and discharge. So I'm effectively creating a longer amount of time that I can put energy onto the system from that plant because I've stored some of that energy. The way that the interconnection agreements are written, there's always going to be a ceiling. So you can't, if you have an interconnection, a generation interconnection with the utility, it's going to cap you on how much you can inject in the system. And so what they're using the batteries for is to not increase nameplate capacity higher. They're using batteries to increase the duration that they can sell power at that same level into the evening. The transmission line voltage is 230 kV. What are the benefits to using a concentrated solar power array unit? The problems compared, what are the benefits or problems using a concentrated solar power array unit? I'm not really sure I understand the question. Is that
They got all the years.
Yeah. I think it's just a technology thing, you know. Those plants, a lot of them went in the late 80s and early 90s, where they use the mirrors to heat up like a sodium type liquid, could hold energy for a long time, and they use it to boil water, turn a turbine. Yeah, nowadays the PV costs have went way down. And so if you have the real estate to spread out the 400 watt panels, the cost is much more appealing, because you don't have to deal with turbine generators, you don't have to deal with the sodium, you don't have to deal with all that. It's a pretty simple system, the PV is. But it used to be the photovoltaic cells were very inefficient. You couldn't generate much electricity. Nowadays, they've come a long ways on their output, and their cost has become much, much more competitive.
So how does temperature affect the solar panels?
Well, it can degrade it. So it depends. It's kind of a cost benefit analysis that the solar plant designer will go through when they're choosing a panel. So there are panels that are more resistant to high temperatures. In other words, they can still produce a higher level of electricity when it gets really, really hot out. There are other panels that maybe you're using in Wisconsin that are not very well designed to accommodate really high temperatures. And so when it gets really hot outside, they actually produce less energy. And so the engineers that are going to work through that process, they're going to do a cost benefit analysis. And there's obviously a cost to procuring panels that are more efficient. There's a cost to procuring panels that operate better, have better thermal characteristics. Some of them are more resistant to external damage, like hailstones and things like that. So that's all part of the design process of the solar plant itself. Then there's going to be an economics consideration on the backside of that. Is it worth spending an extra X number of dollars to get a few % higher efficient panel? Maybe it isn't, maybe it is. And that's just an analysis that the design team needs to work through.
So for this planning in particular, what's the life of those panels and what's the life of those poles that design that person?
The transmission line poles are a 50-year design life on the poles themselves. The panels, I'm not sure. I think they're probably a 25 or 30-year panel, but that may be even a stretch, maybe even closer to a 20-year panel. Yeah. Does that answer your question?
Yeah.
Reactive power support. So I will admit I'm not a systems engineer. The reactive power, what will it provide to the system? Well, generally, reactive power support from renewables isn't great. Unlike a spinning turbine that has coal behind it, or a nuclear reactor can really support that. I'm not sure. So how these usually work, Aaron, is as part of the large generator interconnection agreement, the system needs to meet certain power quality requirements on their power factor. And if the power factor is less than, say, 0.95 or greater than 1.05, we may need to provide reactive support within the substation itself to support that requirement to meet the interconnection requirements. Generally, we're not putting reactive power support in these facilities to sell in the open market to support the system itself. Most often, the energy delivered to the point of interconnection has to meet the specifications of the utility. And if the plant requires reactive support, they will do that to meet the requirements of the
Yes.
DNR requirements come into play for Wisconsin UT lines, absolutely. Environmental requirements are for almost all linear infrastructure, including transmission lines. Aaron asked another good question. What drives the height of the height requirement of the transmission over the aqueduct? That is, that's the owner of the aqueduct. That's what they wanted.
Okay.
Los
What are
Angeles
we doing for dinner?
I have a question following that. Sure. So for we see right of way means not only here, but all the way up to-
Correct.
to the space.
Yeah.
See that?
You're
Because
cooking, right?
you don't
It
need much
sounds like
Can
you're
everybody
cooking.
mute?
requirement.
I'm having beef and broccoli, and you're having one of
Correct.
those.
That's a good point.
Because this is a
those
cost,
egg
right?
rolls.
You go, you ask a lot of 10 things.
All right.
I don't know, that's
All
not
right.
$10,000. It's like, I don't know how many dollars
Yeah.
extra.
Yeah, so it depends on the landowner, right? And what the usage of the
The
property is going to
lumberyard is
be.
open
If you're in
tomorrow at 7
agriculture,
o'clock.
you're probably less concerned about the
You wanna
aerial
try to get
easement
up early and we can
and
go
more
there
concerned
and
about
get it
physically
on the
where
work.
the tower is going to be located. That's going to impact your agricultural operations like farming.
No, I'll take- I'll
If
take
you're a
that.
developer and you want to build a building
Down by,
right
yeah,
next to the
down
right of
by,
way, you want to make sure
Kelly's
that
house in
you
the
can
bottom
do
of
that
that Gypsy Hill.
and have that aerial clearance to do what you need to do.
All
A
right,
lot of times what we'll try to do is
Gary,
on the
can you
aerial
mute your mic?
easements, put the poles next to, say, a road right of way, but put it on private property. And then we'll utilize the road aerial easement. Most DOTs don't care if you use their aerial easement because roads aren't vertical. But that's a very good point.
Until there is strong in the future.
Correct. Yes. Yes.
So I'm curious for the part that has to go underground, because, you know, same thing about the cost, the challenge to build that. I'm curious if you're allowed to see that, why they don't allow you to go.
Oh,
For the
because
underground part.
yeah, maintenance issues again. So those are part of their backbone energy corridors. And so what the owners of those transmission lines, they want to be able, they don't want to have our transmission assets impacting their ability to operate their equipment up and down the right of way. It's similar to what the aqueduct wanted as well. So they want to be able to maintain and operate their facility with impunity, basically. They don't want to have to coordinate with the owner of this transmission line that's in the way of their ability to bring equipment up and down their right of way. So they say, we just want it underground so we don't have to deal with it. So again, that's an owner of the transmission owner is making that request, or that requirement to cross their asset. It doesn't always occur that way. Oftentimes we can go overhead underneath it.
How many miles were underground?
It was not very far. It was like 1,000 feet,
Okay.
maybe. Yeah.
Did you have a substation in the Edwards plant area and the what is it, the Scranton
Sanborn plant.
Sanborn plant?
Correct. There was a collector
So those
sub.
are the-
Yes. So there was a collector substation at the Edwards facility. There was one at another one at the Sanborn facility. And there was, because of the metering requirements, I didn't get into that, but we actually had a switching station in the middle to take 2 circuits from one plant, and 1 circuit from one plant, 1 circuit from the other plant, put them together, the other 2 circuits, put them together. It's the way that SCE used the interconnecting utility one.
So is the point of connection to the grid, that was like west of that location or whatever? Is
Correct.
that another substation?
Correct. That was the utility substation
And that was already there.
that's already constructed. Correct. Yeah. So that's the point we would plug into it.
Those cultural sensitive areas, what are those?
Well, in this case, it was tribal. So was the cultural sensitive
Okay,
area.
that you build around it?
Yes, yeah, we were able to build. They put, it's not as if you build, I mean, it's buffers, right? So they'll have experts that go out there and delineate all of that and identify what is culturally significant. And then they'll mark it out and say this needs to be protected, and then we can then construct around it. Yeah, that's typical. Yeah, I think I wouldn't want a transmission pole or utility on my property. I can't see how that would do anything but lower property value. Oh, they are completely compensation. Absolutely, they are compensated. So yeah, so that's part of the negotiating process. Most of these developers don't have the ability to perform condemnation or take the property. That's not the right way to say it, because you're compensated for it. So it's basically fair market value, and then usually inconvenience costs on top of that. So yes, all of the landowners that have the assets built are compensated per their agreements.
Does this plant store the energy?
It doesn't store much, it does, because it has the batteries, but again, the storage component is to pull that. If we go back to the, if we just go back to the, that's the wrong one.
You extend the service rather than.
Yeah, so if I go back to the
store.
curve, what they're trying to do here is, so you can see this is as the solar begins to go down. Let me move this so you can see. Sorry. So as the solar generation is this orange line, as it's trending downwards. But this is the demand line. It's coming up, right? Because that's the evening time when people are using more electricity. The idea was with the batteries is, can I pull this curve further out?
Mhm.
And so when the facility is no longer generating electricity from the grid perspective, it sees it's still producing because we're discharging the batteries.
So do solar plants use pretty much all that is required, or all that they can make?
Well, it depends on what the grid, so that's where the grid operator comes into it, right? That's what the ISOs are going to do. They're going to tell the plant how much to produce based on the current grid conditions, because not every single power plant can't produce the maximum capacity that it wants to at the exact same time, right? Because that supply and demand need to be in balance. So that independent system operator can come in there, and that's how they help. They can curtail if they need to, but those there are contracts that these companies sign with the utilities and the ISOs to prevent that. So there's orders of curtailment, things like that. But the idea, I mean, they would like to produce. I mean, from a financial perspective, every megawatt they're capable of 24/7, 7 days a week if they could. Let's take a look here. Yep, we talked about the compensation. You mentioned earlier the presentation, often solar power sources.
So if the pole goes through this piece of land, the land belongs to the company now, or?
Well, it depends on the easement agreements. So you can lease the property from the landowners to put your assets on there. Generally, they're going to purchase the right of way, but that purchase is going to have the landowner may still have some rights to it. So the utility can say, we just want to buy a parcel of property and if you go on it, you're trespassing. Or they can buy the property and still provide the rights for the farmer to continue to farm on it and do activities underneath it. So there's a lot of different types of agreements that can be hatched with the landowners based upon usage of the property, planned usage of the property, and things like that.
That's a difference between, let's say, railroads, right?
Right, yeah.
Because railroads, you have to buy this whole.
Correct.
So nothing can go through it, so.
Yeah, so for example, if it's an agricultural, if you're in an agricultural zone, a lot of things that the agricultural people are concerned about is their ability to farm. You know, how does that impact my tractors, the spacing of the poles? Am I going to be able to get my equipment in and around it? In Wisconsin, there's a thing called stray voltage. Maybe you've heard of that. So there's some concerns about, is there some voltage issues that may affect milk production? But generally, you can keep the land pretty much productive. The only real negative, well, I shouldn't say the only real negative, that's not true, but one of the biggest, from negative is the fact that we have to clear the trees. And so trees and power lines, they don't go together. And so if you're in like in Wisconsin, you want to build the power line, you're gonna have to cut the trees down because you can't have trees and power lines together. And that can be pretty impactful to the view sheds and to the area. In this particular location, there's a lot of Joshua trees that are illegal to cut down. And so there was that other component to it as well, to avoid Joshua trees.
All right, so here, before we continue here, I'm gonna do this. It's already 6:06, so I'm gonna officially close the seminar.
Okay.
But we will continue discussing until we'll finish all the questions. So you have to some other things to do. Feel free, to leave. Don't worry. But we will continue until we finish all the questions. And then same as Zoom. So thank you again for coming. Take some cookies. Yeah, thank you very much. All right. So yeah, I think Mike, if you have time. Let's
Yeah,
finish
sure,
the
absolutely.
questions. Yeah.
Okay, so the next question from Brent talking about, I think what you're getting to is distributed generation, basically putting generation assets out at near the point of usage. Good. Yeah, that's definitely something that's going on. Instead of building these large, massive plants, generating a large scale of energy, say, what if we build a whole bunch of small plants really close to the load centers, close to the usage? You know, easy example of that is on like the Walmart rooftop, putting a whole bunch of solar panels on top of the Walmart rooftop. There's challenges with integrating the distributed generation from makes another level of complexity, but I think what you'll be seeing is, especially in areas where the sun shines maybe a little bit more than Wisconsin, that we'll see more and more of the distributed generation going out there. There is, on that distributed generation components, depending upon what if it's just your house, you certainly can generate enough electricity to power your house from a solar panel and a battery system.
This is almost over.
You may not be able
my
to run your air
webinar.
conditioner full steam
But
24/7,
are you gonna
things
be
like
here
that. But
for a little bit?
for large manufacturers, sometimes there just isn't enough. You can't
Wait.
generate enough on site or nearby
Oh.
to meet your demand, so you still need that grid connection. The future expansion was factored into the design of this project. Yes, it was. As always, people always want to maintain their options. So there is ability to add additional bays in the substations, and there is upside capacity on the transmission line to push more amps.
Is the whole plant, is this phase done? Like,
It's energized and producing. Yeah, they're still adding to it, primarily on the battery side. The battery integration is complicated. I mean, I'm not a programmer, but to get there's a lot of components on the battery side. You've got one system that's just doing conditioning of the batteries. You want the batteries to stay within a certain thermal range, and you want to manage how fast they discharge and how full they charge. Just like your cell phone, if you aren't good with your battery, you may degrade your battery over time. So there's a battery management system that comes from the factory that's going to manage the battery. And then you've got another we call master power plant controller, which is going to control how much generation is going on at the solar plant, where that's going. It's controlling, because you may have multiple different manufacturers of inverters and solar panels, and you have to bring all that together in a cohesive system. So you have a master power plant controller, which is talking to all of the inverters and determining, where that energy is going to go within the substations. And then it's also going to communicate with the batteries as well. Then on top of that, you're going to have the ISO, the Cal ISO, that's going to be issuing commands too and say, the grid needs this much power, the grid needs less power, the grid needs this much power. And so when that call comes, that's going to go to the master power plant controller. Master power plant controller is going to dispatch to the individual panels and the batteries. That command may be in conflict with the BMS system, the battery management system. The battery management system may say, hey, we don't want to discharge right now because we're running too warm, or we don't want to charge because we're too warm, or whatever reason. So those algorithms and how to control that become more over my head. We have folks that specialize in programming those systems, but it's not my expertise. Yeah, I think that this Charles Brooks, this is a good question. It's exactly what they're trying to do. Right now, the issue is just a numbers situation. So again, if you look at the curve here, this is the solar generation. There's still 7,000 megawatts of demand that's needed that's not being fulfilled by the solar plant. So it's every megawatt that's being generated by the solar plant could be sold in the open market, and it is being sold in the open market, except for what they're trying to do on the battery side by charging the batteries in this area solely so they have some backside discharge capability. But so this project is going to your point that if I can produce maybe to this way up here, a whole bunch of solar, and I have a whole bunch of batteries, theory would say that I'm generating a bunch of surplus solar, I can charge those batteries, and I can go to a net zero grid, which I think is where California is trying to go. This is just that snapshot of where they're currently at.
So based on that graph, if we want to achieve the lead, you know, the goal you set there, how many more of such scale we have to put?
Well, let's see, I mean, right now we're looking at having about 12,000 megawatts of generation. And you've got about at this time 22,000 megawatts of total demand. So you're roughly halfway there.
So just one more of such scale than we're it?
Well, probably 10 more of these ones we just built.
10 more.
Yeah. And that doesn't include what's going on out here with the peak, but on the low, yeah. A lot. And then there's issues, you know, I think, you know, we do run into available land. Again, this project is relatively close to an injection point. If you go out in the middle of the desert, you may be a long ways away from the nearest place to interconnect. And then building 20, 30, 50, 100 miles of transmission line can make the project no longer financially viable. Let's see, I think we're to the bottom of our chats. It's got 15 people on, maybe those people that have questions. Okay. No, the DC owner doesn't have to pay the difference because the DC owner is in no position to, it's our project. So they just are given that requirement. So that's the cost to do the underground in this question is borne by the developer, and this goes into the overall project cost. Yes, on the last question from Charles Brooks, yes, there is battery only systems. In fact, Cal ISO has put a call out, an RFP out to developers to provide pure battery only. And so we're seeing developers going to, in urban areas, empty lots or just areas of opportunity and putting in 50 megawatt, 100 megawatt hour battery facilities just to meet Cal ISO's request RFP for additional battery energy. And that is exactly what you've described, where they would charge those batteries often at low demand where the energy per kilowatt hour is less and sell it at a high demand when the energy costs are higher. But since there's also the RFP is coming from the grid operator is basically saying we want more battery. From the curve we're just talking about, you can see why they want more battery. There could be opportunities to negotiate even better rates when you sell back to them at specific times of the day. So yes, that's exactly what's happening as well.
All right.
I think that's all the questions.
That's all the questions?
I think so.
Okay.
I didn't miss
All
anything.
right. Well, thank you very much.
Well, I think the problem was, well, I'm gonna stop recording first. Stop recording.